Today we are going to learn about limit of Riemann sum. We will start with summations. So first of all, first example, write each using summation notation. We have 2 to the third power plus 3, 2 to the 7th power plus 3 to the 7th power plus 4 to the 7th power plus 5 to the 7th power plus 6 to the 7th power. We can write it using summation notation. We can say n is equal to, we can say I equals 2 to 7, and we have I to the power 7 here. I to the power 7. I equals 2 to 7, I to the power 7. Next example, part B, we have 2 square plus 2, 3 square plus 3, 4 square plus 4. So that would be I is equal to 2 to 5. I equals 2 to 5. I square plus I. I square plus I. I square plus I. Next, we have e to the power pi plus e to the power pi over 2 plus e to the power pi over 3, all the way up to e to the power pi over n. I is equal to 1 to n, e to the power pi over n. Next, we are calculating each sum. So let's first remember summation formulas. Here, we have summation I equals 1 to n of c a of I. We can pull the constant out of a summation. So if we have summation of two different functions, we can do two different summations and add them up. Sum of two different functions, summation of a sum, we can do sum of summations. And summation I equals 1 to n of c would be c times n. C is a constant, would be c times n. Summation I equals 1 to n of I would be n times n plus 1 over 2. We can use it to find the sum of first 100, first 2000, first 50,000 numbers. Summation I equals 1 to n of I square would be n times n plus 1 to n plus 1 over 6. Summation I equals 1 to n of I to the third power, n square n plus 1 to the second power over 4. Okay, so let's see some examples here using these summation notations. So this is the one where we can use the constant rule. So this is like I equals 1 to 5, 3. So that means we're going to be doing 3 plus 3 plus 3 plus 3 plus 3. We could just do the summation formula we just saw, that is going to be c times the n, 3 times 5, which is 15. Next, we have I is equal to 2 to 4k squared. The formula wouldn't work here because my k is starting at 2 here. So I'm going to go ahead and do, or we can use a formula and then subtract something from it. But it's not really a lot of work to just go ahead and start plugging k as 2, k as 3, k as 4. 2 squared is 4, 3 squared is 9, 4 squared is 16. So that is going to be 29 plus 4, which is 29. Next, we are given a1 is negative 5. Summation I equals 1 to 10 of ai is 20. Summation I equals 1 to 10 of bi is 7. And we want to find out this. Both will be similar. I'm just going to work on one of these. So let's see if I were to look for this. I is equal to 1 to 10 for ai plus I is equal to 1 to 10 of 3. Now here we can just use the rule that we learned about the constant. So that's going to be 30. That part would be 30. And the first part, I can pull the constant 4 out if I want and do the summation ai, I is equal to 1 to 10. And I already know ai is equal to negative, a1 is negative 5. Summation I is equal to, so this part is equal to 20. So if I pull the 4 out, this would be 4 times 20 plus 30. 4 times 20 is 80 plus 30. 80 plus 30 is going to be 110. Next, use the summation formulas to evaluate the limit. So remember the formulas that we just talked about. Memorize these formulas. We will be using these over and over. Summation formulas here. They will be used a lot when we are evaluating the limit of a Riemann sum. Let's go back. We want to use the summation formulas to evaluate this limit. Okay, so limit n goes to infinity. Summation I is equal to 1 to n, I over n squared. Now, n goes to infinity. I can pull out 1 over n squared from here. 1 over n squared out of the summation. And then we have I goes from 1 to n summation. Now this, we can use the summation formula. This is equal to n times n plus 1 over 2. So n times n plus 1 over 2. We can say this is limit. N goes to infinity. 1 over n squared, n times n plus 1 over 2. Let's see what can be cancelled, or even before something that can be cancelled. So this is 1 over n squared. That would be n squared plus n over 2. Let's distribute 1 over n squared and see where does it take us. Limit n goes to infinity. 1 over n squared times n squared over 2 plus 1 over n squared times n over 2. Now we can get rid of this here. So it turns out to be limit n goes to infinity 1/2 plus 1 over 2n. When n goes to infinity, this term is going to go to 0. So the limit turns out to be 1/2 in this case. The limit would be 1/2. We are evaluating these limits because when we are evaluating the area using Riemann sums by taking the limit n goes to infinity, we will be looking at some similar functions. Next, evaluate the limit n goes to infinity summation I equals 1 to n for this function. Okay, again, I'm going to pull out n to the third out from the summation. N goes to infinity, 1 over n to the third. We have summation I squared, I is equal to 1 to n, minus summation I is equal to 1 to n of I, plus summation I is equal to 1 to n of 1. We are going to use all the summation rules here. We have a rule for I square, rule for I, rule for 1. So limit n goes to infinity, 1 over n to the third power. Summation I equals 1 to n of I square. What is that going to equal? That one is n times n plus 1 over 2. No, that's n times. That's not n times n plus 1. This is n times n plus 1 times 2n plus 1. So n times n plus 1 times 2n plus 1 divided by 6. That's what summation I square formula is. That's how you can find the sum of first squares of first 100 numbers or first 2000 numbers or whatever n you want to plug in. So this is the formula we just used. Minus summation I is equal to 1 to n of I. That's n times n plus 1 over 2 plus this is going to be the constant 1. Now let's go ahead and simplify and see where does this limit go. 1 over n to the third, n times n plus 1. When I multiply, that would be n squared here, n squared plus n, and I'm multiplying it with 2n plus 1. So n squared plus n, 2n plus 1 divided by 6 minus n squared plus n over 2 plus n. Again, cleaning up, simplifying, and see 1 over n to the third. N squared plus 2n would be 2n to the third plus n squared plus 2n squared plus n over 6 minus n squared plus n over 2 here over 2 plus n. Okay, now we can go ahead and bring the n to the third inside. And there are some like terms here that I can combine. This would be 3n squared. So we would have limit n goes to infinity 1 over n to the third times 2n to the third over 6 plus 1 over n to the third times n to the second over 6. Actually, it's going to be 3n to the second plus 1 over n to the third times n over 6 minus 1 over n to the third times n squared over 2 minus 1 over n to the third times n over 2 plus 1 over n to the third times n. Okay, now go ahead and cancel everything we can here and then see where does it take us. N to the third, so that's going to be leaving an n squared in the denominator, leaving an n to the second power in the denominator, leaving an n in the denominator, leaving n squared in the denominator, leaving n squared in the denominator. So looks like this limit is going to go to all the terms where I have n in the denominator. I don't have any n's in the numerator, but n in the denominator, all these terms are going to go to 0. Because when n goes to infinity, n gets really, really large. First term is the only one where I don't have any n's. It's like same degree in numerator and denominator. So that limit, this limit goes to 1/3. So we use the summation formulas here, memorize the summation formulas. Next, we're going to look at left-handed Riemann sum and right-handed Riemann sum. So left-handed Riemann sum would be limit n goes to infinity, I equals 0 to n minus 1, delta x times f of xi. Now, we estimated the area using Riemann sums, finite Riemann sums, but we saw that our estimate was not very good because the more number of rectangles we use, the better approximation we get. So now we're going to be using infinite number of rectangles. So we're going to say limit n goes to infinity. And for the left-handed sum, we do use the very first height, right? That's why we're starting with a equals 0, your first point. And then we go all the way to n minus 1. That means we don't use the very last height, which is the nth height. We start with the 0th height. And we don't use the very last height, the nth height, but we use n minus 1. So left heights are being used. And this is the width of each rectangle times the height of each rectangle. Now for the right-hand Riemann sum, we start with the very first height. We don't use the 0th height, but we do use the first height. And we do use all the way to the nth height. So this is the scenario we have. This is going to be your 0th height. This is going to be your nth height. So if this is the point A and point B, and I'm just drawing that this is how my function looks like, for example, and we want to find area under the curve here. So for the left-hand sum, we would end up using A-th height. We're going to call it 0th height. And we wouldn't be using the very last height. For the right-hand sum, we're not going to use the very first height, but we're not going to use the 0th height, but we're going to use the first height, which will be somewhere here. And then we would end up using the very last height. Okay, so that's the right-hand Riemann sum. And normally, if you do both left-hand and right-hand Riemann limits, they're going to come out to be same. Because summation formulas start at I equals 1 to n, or I equals 1 to n, they are going to be easier to use with the right-hand Riemann sum. So anytime we're evaluating the limit of Riemann sum, I would be using the right-hand Riemann sum. And right-hand sum and the left-hand sum turn out to be same when you use really, really large number of rectangles. So limit definition of integral. The area under the curve can be defined as the area equals limit n goes to infinity, summation n is equal to 1 to infinity delta x f of xi. Delta x is the width of each rectangle. Let's see this formula in action. So here's first problem. Find the limit of Riemann sum f of x is equal to 1 minus x squared over 0 to 1. Okay, so this is the formula that we just saw. This is how we can find the area under the curve. So let's start with what's going to be the delta x in this case. Delta x is going to be 1 minus, delta x is always b minus a, the point b minus a over the number of rectangles you have. So it's going to be 1 minus 0 over n, which is 1 over n. Okay, so we found the delta x. Now the piece that we need to figure out is f of xi. F of xi. Xi is equal to a plus I delta x. So the very first height, when we're looking for height number 1, it's going to be the a plus 1 increment. So that's the piece we need to understand here. I is equal to 1 to n. We're not going to be using the 0th height, but we're going to be using the first height, which is going to be a plus whatever the small increment we are looking at. So xi is equal to a plus I delta x. In this case, xi would be, xi is equal to a plus I delta x is 1 over n. We just found that. So a point, this is my a, this is my b, a is 0. So delta x would be, or xi in this case would be I over n. Xi would be I over n because it's a plus I delta x. A plus I delta x, and we know a is 0 plus I times 1 over n. So we can say xi is equal to I over n from here because we don't need to add 0 to it. Xi is I over n. Now we need to find out f of xi. F of xi would be, the first height, the second height, the third height, the fourth height, and we're going to infinite rectangles. So for the first height, now we know what xi is, whatever f of x we are given. So f of xi would be 1 minus, we're going to replace I by xi. This is xi. We're going to replace I by xi. We're going to replace x by xi in this function. So it's going to be 1 minus whatever xi is, that's going to be I over n to the second power, which is 1 minus I squared over n squared. 1 minus I squared over n squared. Okay, that was the only harder part here. Once we have that, we are ready to go ahead and take the limit and use the summation formulas. N is equal to 1 to infinity. Delta x is 1 over n times f of xi. If we just found 1 minus I squared over n squared. Limit n goes to infinity, summation n is equal to 1 to infinity. That's 1 over n minus I squared over n to the third power. Okay, I'm going to separate it into two different summations. And limit n goes to infinity, limit n goes to infinity, we would have, that's a too big of a summation. We would have summation n is equal to 1 to infinity, 1 over n minus summation n is equal to 1 to infinity, I square over n to the third. Okay, for this, n is some constant, n is the number of rectangles. It's really large number. We don't know what it is. So I'm going to pull the constant out of my summation. That's going to be n is equal to 1 to infinity of 1 minus 1 over n to the third. N is equal to 1 to infinity of I squared. Okay, now let's use the summation formulas here. We can use the summation formula here and the summation formula here. So limit n goes to infinity, 1 over n times summation n is equal to 1. Oh, it's going to be, sorry, all these are going to be going from 1 to n. All these are going to be going 1 to n. Yep, summation goes 1 to n. And then we take the n 1 to n. Okay, there we go. That's fixed now. Summation 1 to n. N is equal to 1 to n. Summation n is equal to, oh, it would be I equals 1 to n. Let's go back and fix it. So that's going to be summation I equals 1 to n. I equals to 1 to n. Go back and fix it. I equals 1 to n. Okay, now it looks good. I equals 1 to n. I equals 1 to n. I equals 1 to n. All right. So n is a constant for this summation because this summation involves the i's in there. So I can pull out 1 over n here. So when I use the formula in the first one, I equals 1 to n here as well. I equals 1 to n. Only then we can use the summation formulas. So 1 over n, this is going to be n minus 1 over n to the third. I square is n times n plus 1 times 2n plus 1 over 6. Now, cleaning up, limit n goes to infinity. This part is just going to be gone. So that's just a 1 here. Minus, did we also pull out something in the beginning? Nope. So looks good so far. Here we have n times, so 1 over n to the third times n squared plus n times 2n plus 1. We just did that in the previous problem. We did multiply them, and that turned out to be 2n to the third plus 3n squared plus n. 2n to the third plus 3n squared plus n. 2n to the third plus 3n squared plus n divided by 6. Okay, limit n goes to infinity, and it's lowercase n in this case. All right, so now I have 1 minus, let's go ahead and distribute n to the third in there. So this becomes 2n to the third over 6n to the third minus 3n squared over 6n to the third minus n over 6n to the third. Now, if I look carefully, these will be cancelled, but all these terms, when n goes to infinity, because I'm going to have n's left in the denominator, these terms are going to go to 0. So I'm left with 1 minus 2/6, which is 1 minus third. That comes out to be 2/3. So area under this curve, f of x equals 1 minus x squared. How does this graph look like? It's a parabola, and it's inverted. It's, shifted 1 unit up, and it's flipped. It's opening at the bottom. So this is the area we just found. Actually, we just looked from 0 to 1. So we didn't really find the area for this region. We only looked for the region 0 to 1. So this is the area we just found using. And you can see the area turns out to be 2/3. And there's no other way other than, this is the beauty of calculus, that we can find the area under a curved surface that doesn't look like we are able to. And it's not a circle. It's not a part of circles. We can now use the formula for circle to estimate this area. Let's see another example. Evaluate the limit of Riemann's sum. Here again, I do have a parabola. This one is shifted 1 unit up, and we're looking from 0 to 2. So this is the area we're looking for, right? So the formula is limit n goes to infinity. limit n goes to infinity, summation I is equal to 1 to n delta x f of xi. Now, the harder part is, first of all, let's see what delta x is. Delta x is going to be b minus a divided by n, which is going to be 2 over n. F of xi is going to be f of a plus I delta x. That's your first point plus how many increments you are using. So that's going to be f of a, which is 0, a is 0, plus I times delta x, we just said is 2 over n. So we want to find out f of 2I over n. We know what f of x equal to. So if I replace the x by f of xi, f of xi would be x squared plus 1, which is going to be 2I over n squared plus 1. Now let's plug this into the formula. Limit n goes to infinity, summation I is equal to 1 to n. We are going to replace the delta x by 2 over n and f of xi by 4I squared over n squared plus 1. All right, almost there. Looks like n is equal to, limit n goes to infinity. So first of all, limit n goes to infinity. Do not drop the limit. Keep bringing it down until you apply. So we have 2 over n, 4I squared. Let's distribute 2 over n inside and then clean up. So that would become 8I squared over n to the third plus 2 over n. All right, limit n goes to infinity. Summation n is equal to 1 to infinity. I'm going to pull 8 over n to the third out. 8 over n to the third out from the first summation. I'm going to write it as two different summations just to be able to use the formulas. 8 over n to the third, summation n is equal to 1 to infinity, I squared plus summation n is equal to, I is equal to 1 to n. Summation I is equal to 1 to n. Okay. Summation I is equal to 1 to n, I is equal to 1 to n, and I have 2 over n. I can pull out the 2 over n from here. So if I pull out the 2 over n, I have summation I is equal to 1 to n of 1 here. Okay, so we know this is going to be equal to n. So this is 2 over n times n. 2 over n times n for the second part. And let's see, what are we left with the first part? We can use the same summation formula that we just found. We did use it in the previous two examples, and we actually multiplied. So this is going to leave me with 8 over n to the third. This is n times n plus 1 times 2n plus 1 over 6. Okay, cleaning up, I'm just going to steal the multiplication or find out what I multiplied, what I got after we multiplied in the last example. So limit n goes to infinity. This was, this turned out to be 2n to the third plus 3n squared plus n. 2n to the third, 3n squared plus n over 6 plus a 2. Okay, limit n goes to infinity. Go ahead and distribute. So we have 8 times 2 is 16. 8 times 2 is 16, n to the third over 6 n to the third, plus 8 times 3 is 24 n squared over 6n to the third, plus 8n over 6n to the third plus a 2. Okay, cleaning up, these are gone, and all these terms are going to have an n left in the denominator. Both of these terms are going to go to 0 when n goes to infinity. So I'm left with 16 over 6 plus 2. 16 over 6, let's go ahead and simplify 16 over 6. That turns out to be, 16 over 6 is 8 over 3. So we can write it as 8 over 3 plus a 2, which is going to be 6 plus 8 is 14 over 3. So that's my area under the curve for this graph, looking at the point 0 to 2. And that's the fun. That's the interesting thing, that doesn't seem like we can find this area using geometry or any other formulas, but calculus helps us estimate the area by dividing it into infinite number of rectangles of very, 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 very small width, and we have the area under that area under the curve. So that's the area between the x-axis and below that curve, looking for the interval 0 to 2. That's all for this video. So we saw some summation formulas and how to find the Riemann sum or area under the curve using the limit of the Riemann sum.